Let's continue right away. It is my great pleasure to introduce Jan-Philipp Solovej. Jan-Philipp is, as you know, one of the recipients of this year's Henri Poincaré Prize, and as such, he has been introduced in detail on Monday. So I'll be very short. Jan-Philipp obtained his PhD in 1989 under the supervision of Elliot Lieb at Princeton University, and after several steps in the US and Canada, he returned to Denmark, first to Aarhus, and since 1997 he's a professor of mathematics at the University of Copenhagen. He's also one of the directors there of the newly founded Willum Center for the Mathematics of Quantum Mechanics. A large part of Jan-Philipp's work is on the mathematical analysis of quantum many-body systems, where he has made many fundamental contributions. He's, I think, particularly well known for developing the necessary mathematical tools for putting Bogoliubov's approximate theory on a rigorous mathematical footing, and I think this is also something that will feature prominently in his lecture this morning on the ground state of the Bose gas. So Jan-Philipp, before you start, let me also hand over this gold, I'm not sure, but in any case, medal for plenary speakers, and we're looking forward to your talk.
Thanks a lot. So can you all hear me? It's on? Okay, very good. So thanks a lot, Robert, for a very nice introduction, and thanks to the organizers for inviting me to give this talk, and of course to the Henri Poincaré Prize Committee for giving me the Henri Poincaré Prize. So what I will talk about today is the ground state of the Bose gas. In fact, ground state of Bose gas is because it's a very general result that I would like to talk about. Sorry, I should go back here. So my talk will be that I will first introduce the. I need to find out how to use this this thing here. Okay, okay. I figured it out. So I will talk about many-body Hamiltonians with two-body interactions. This is sort of the most basic type of many-body quantum Hamiltonian you can have. I will be studying things in the thermodynamic limit, so meaning that I will go to a box of infinite size and have a finite density of particles. And my main concern will be the ground state energy of this. So if you want, I'm thinking of zero temperature of such a gas, and I'll try to understand what is the state, but more precisely, I will try to understand what is the ground state energy, and from that, infer what the state is. I will start by talking about the two-particle case and define what's called the scattering length. If you want to think about it, I mean, if you have a quantum system of two particles interacting, we know we can do the center of mass reduction and think of it as a one-particle problem, and we basically know how to solve this, or at least replace it by a spectral problem. So that's the simple case. That's the n=2 case, two particles. But then I want to study the infinite many-particle case, but with finite density in a large volume, and I want to see how much of that can actually be inferred from just knowing how two particles interact. And for that, it's relevant that we're looking at the dilute limit, right? So you will think of a situation where there are few particles per volume. And I'll make precise what I mean by that. And in that sense, sort of the leading order will be coming from the two-particle effect. But we will see that even the correction to that is what is also given by the two-particle interaction, and that's the famous Huang Yang formula, and I will explain what that is and how it gives a correction to the first-order energy, which comes just from understanding what's happening with two particles. This has been verified experimentally, or at least a little bit verified experimentally in a few cases. The fact that you can do an expansion of the energy up to second order knowing only how two particles interact with each other. I will explain the different rigorous results, but in particular, I will give the main theorem, which is joint work with Søren Fournet from Aarhus University, as I stated there on the front page, which is a proof of this Huang Yang formula, the correction to the ground state energy beyond what you would expect from just looking at two particle interactions. I will then go a little bit into the heuristics behind it, how it's related to Bogoliubov theory, Bogoliubov's famous theory of superfluidity going back to 1947. Both I will explain how it, in some sense, does give the formula that we are trying to prove, but also what is missing in what Bogoliubov did, the famous Bogoliubov approximation, which does not quite give the formula. You have to correct it to make it the true formula, and I'll explain how that works. And I will go through the rigorous argument of the proof that of the theorem that we have. So here is the situation. So we are looking at a two-body Hamiltonian. So, I mean, an n-body Hamiltonian, sorry, with two-body interactions. So in a sense, this is the most basic many-body Hamiltonian you will have in physics. You have a kinetic energy term, which is the Laplacian. You have n particles. I'm putting the n particles in a box of size L, but I will soon let L go to infinity to think of it as being in the infinite volume limit. So we have n particles. They have the free part is the kinetic energy, and then they interact two particles at a time with a potential that I call V. Now, I'm going to make very few assumptions on this potential. The main assumption is that it's positive, so it's a repulsive potential. That's the only case that we can treat. I'm also assuming that it's spherically symmetric, but beyond that, I'm making very few assumptions. So it could even take the value infinity. For the talk here, I will restrict myself mainly to potentials of compact support, but we can even relax that. I mean, we can almost take potentials that are only L1, I mean, integrable at infinity, not quite. We need a little more decay than that. But for this talk today, not to get into difficult assumptions about the range and the decay of the potential, let me assume that it's compact support. But other than that, it can be infinity, so a particular important case is the hardcore potential. And that's simply the potential where the particles do not see each other unless they are at distance a from each other, and then it's a hardcore. So they cannot get closer to each other than distance a. So that's what's called a hardcore potential. That's sort of the strongest potential one could have in mind. So that's one example of the two-body potential that I will be looking at. Now, the Hilbert space, I said it was the Bose gas. And the Bose gas means that we're looking at what I wrote here. It's the symmetric tensor product of the L2 space over the box omega L. But in fact, it turns out that if you don't make any symmetry assumptions, you don't actually have to talk about bosons, because if you restrict it just to the full L2 space, for the ground state, it will actually be bosonic. It will be symmetric. The ground state is unique, and since it's unique, it's actually symmetric. So in a sense, I didn't even have to say Bose gas. I could have said the ground state of this Hamiltonian on a full L2 space of n particles moving in this box, omega L. But of course, physically, particles are either fermions or bosons, and then I'm really looking at the Bose gas. And as I said, I'm interested in the ground state energy. So the smallest energy that I can have on this Hilbert space that I'm looking at, as I pointed out, it's the same for both the Hilbert spaces, either the space without a symmetry restriction or the bosonic subspace of symmetric functions. And the important thing is I want to go to the large volume limit. So I want to let L go to infinity, keeping the density fixed. I'm doing 3 dimensions, n over L cubed should be the density, rho. I let L go to infinity, n go to infinity in such a way that n over L cubed converges to a density rho. It's not very difficult to see, at least if the potential has compact support, as I was saying that I would be looking at here, that this thing has a limit if I look at the energy per volume. So that's what I wrote down there. I take the ground state energy, but I divide by the volume. So I'm looking at the ground state energy per volume, and then I let the L go to infinity, the volume go to infinity, and then I get a function E of rho. It's a function depending only on the density. And that's the function I'm interested in understanding. So, as I said, I would like to understand this in the dilute limit, in the case where there are few particles per volume. And again, I'll make it precise in a moment. And if there are few particles, you would think that the important or the main contribution would come from how two particles interact with each other. So I will introduce what's called the scattering length from the energy coming from two particles. So actually looking at the case n equal to 2, where I have two particles still in the large box. Of course, if I'm picking only two particles and I take the box going to infinity, well, then I'm not going to get a limit because the density will go to 0. But I know how it goes to 0, at least if I pick periodic boundary conditions. Maybe I should have emphasized that we can do periodic boundary conditions, or we could do any other kind of boundary condition. When we do the limit L going to infinity, the boundary condition will not matter for the function E of rho, the thermodynamic limit of the energy per volume. But the energy, if you have just two particles, this is not the energy per volume, this is the energy for two particles. As you let L go to infinity, it will behave like some number divided by L cubed. A number, or rather a length, because the energy in my units will be a unit of 1 over length squared. I mean, I'm putting the Planck's constant equal to 1, and I'm putting mass of particles equal to 1. I'm using such units, and in such units, energy will be measured in the same dimension as 1 over length squared. So I want 1 over length squared as the energy. As L goes to infinity, it's not very difficult to see that if you have as L goes to infinity and n is kept fixed, the energy will behave like 1 over L cubed. And this number in front, well, we are normalizing by an 8 pi, and that number is called the scattering length. So 8 pi a over L cubed is the leading contribution to the energy for two particles as L goes to infinity. So that's my definition of the scattering length. Well, there are other ways to look at the scattering length, because I can actually more or less say what is the function that will achieve this energy. And it's written here. It's essentially a translation invariant function. So it's a function u of x1 minus x2. And that function u is what's sometimes called the scattering solution. It's the zero energy solution of the Schrödinger equation with the potential V. Now, the 1/2 that you're getting here is actually coming from the fact that I'm looking at two particles and I'm looking at the reduced mass, right? I'm looking in the, if you want, in the center of mass problem. So the function u that I'm looking at is actually the function that will give you zero energy there. Now, this function, I'm normalizing it so that it goes to 1 at infinity, and then the function will be between 0 and 1. It's the scattering solution. It will go to 1 at infinity, and it will be between 0 and 1. I'm writing it as 1 minus omega, and this omega will be important later on in the talk. That's the correction from the 1 by the scattering solution. How if there was no potential, it would just be a 1, and you would get 0, right? Because that there would be no correction to just putting the function at 0 energy if you have periodic boundary condition. So the A here, A over L cubed, is the correction you're getting from the potential. It's given by this scattering length. Now, one can find the scattering length from the scattering solution u. In fact, it's the integral of V times u. So the V times u was here. U was the scattering solution. Remember, I told you that u was between 0 and 1. V is a positive potential. It's a repulsive potential. So, in fact, the scattering length, 1 over 8 pi integral Vu, is less than 1 over 8 pi integral V. in particular, if you had looked at the hard core, then the integral of the hard core, I mean, the hard core is infinite from 0 to radius a, so the integral will be infinity. However, the scattering length for the hard core is the core radius, a. I called it a because it turns out to be the same as the scattering length. So this thing will actually be finite. It's a somewhat singular situation, but a will be finite, but the integral v will be infinity. And we'll see that this difference will come in, the difference between the scattering length, which is finite even for the hard core, and the integral of v, which can in principle be very, very big. It can even be infinity in the cases that I will be looking at. Okay, so here are the different length scales in the problem. So I introduced the scattering length. So you should think of the scattering length A as being the relevant length scale for the potential. So think of it, for the hard core, it was the radius of the core. In general, just think of it as the length scale set by the potential. Then there is the interparticle distance, which in 3 dimensions is rho to the minus 1/3. I mean, the density to the minus 1/3. And then there will be another length scale. I mean, there are other combinations of A and rho that will also give you the dimension of a length. And there's a particular length scale which is very important, which is called the healing length. I will explain later where it's coming from, but I just want to mention it now already. It's rho a to the minus 1/2. That's also a length. And it will play a big role when we want to understand the correction to the ground state energy beyond what you would expect from just having two-particle interaction, the interaction of two particles. Now, the dilute limit I can now make precise. The dilute limit simply means that the interparticle distance is much, much longer than the scale set by the potential. Right? So basically, it means that particles just see each other a pair at a time. Right? Because having 3 particles come close is very, very unlikely. Now, the dimensionless measure of the diluteness is this rho a cubed. That's a dimensionless number. The dilute limit means that rho a cubed is much, much less than 1. But I want you to remember one thing, and that is so that what I just said was that A is much, much less than rho minus 1/3, but the healing length, which will play a big role later on, is much, much longer than rho minus 1/3. I mean, if you just look at this thing here and you turn it around and calculate it for rho a to the minus 1/2, you actually see that the interparticle distance is between the scattering length and this healing length. And it will turn out that particles will correlate on the scale also of the healing length, which is a length scale where you will see many, many particles. So I tried to say this here, and at this point it may be a little unclear what I mean by this, but we talked about the scattering solution a moment ago. The scattering solution is sort of the correlation function between 2 particles if you had only 2 particles. Right? I mean, I had this moment ago here. This was this function there. But when you're looking at the many particles, then there will actually be a correction to how 2 particles correlate with each other. Because at some point, when the 2 particles that are correlating are at a very long distance, then there are many particles in between, so if they see lots of other particles, which will create a correlation, and that's happening on the scale of the healing length. And I'll try to explain that as we go along. Okay, so now let me come to the ground state energy. And what would you expect in the dilute limit? So as I said, in the dilute limit, you would expect that you see sort of 2 particles at a time. So it's a natural, sort of intuitive assumption or an expectation that the energy of n particles would be the number of pairs times the energy of 2 particles. That's what I tried to write here, so that the E of rho is the limit, this limit that I've been looking at, L going to infinity, with the density converging to rho, of the number of pairs, n times n minus 1 over 2. I'm dividing by the volume. Remember, I'm interested in the energy per volume. And then the energy of the 2 particles. And we had the energy per 2 particles. If you remember, this was on the 2 slides ago. I had it there. It was 8 pi a over L cubed. And if I simply plug this in, at this level, number of pairs times the energy of two particles, then you will see as L goes to infinity that this will converge to 4 pi rho squared A. Simply from the definition of what the scattering length is. So one would expect that in the dilute limit, that the energy of this gas in the thermodynamic limit, the energy per volume, would behave like 4 pi rho squared A. So a heuristic argument arriving at this conclusion was given already by Lenz in 1927, I mean very early in the history of quantum mechanics. It was proved rigorously as an upper bound by Dyson in 1957. So Dyson actually proved that this is indeed true as an upper bound. He couldn't quite get it also as a lower bound. His lower bound was off. He got it with the wrong constant here. And actually, it took several years, several decades after 1957 before Lieb and Ingwerson in 1998 were able to prove this leading term, meaning getting also the lower bound, and then matching it with Dyson's upper bound. They had actually proved that this was the correct asymptotics to leading order in the dilute limit. But interestingly, in 1957, essentially in the same issue of Physical Review as Dyson's paper, Li, Huang, and Yang wrote a paper where they suggested that there's even a correction to the 4 pi rho squared A, which also depends only on the scattering length. And for this reason, the reason that it depends only on the scattering length, it's sometimes referred to as the universal behavior. So the energy, even the corrected energy, beyond what you would expect from the leading term, also depends only on the scattering length. And here is the formula that they suggested. This is the famous Li, Huang, Yang formula, and that's what the rest of my talk will be about. So there's the 4 pi rho squared A, and then there's a constant. I mean, there's the 1, that's the leading term. And then remember the diluteness parameter rho A cubed. So it comes in with the square root of rho A cubed times the constant 128 over 15 square root of pi. I will explain where this constant is coming from. And then there's a correction, which is lower order in the diluteness parameter. So I talk about this term as the Li, Huang, Yang, or LHY correction. And I say it's universal because it depends only on the scattering length. It depends only on the data coming from two particles. Now, there's even work suggesting that this is true beyond this term, but I'll come to that in a moment. And to come back to the healing length, remember I had these different length scales, the scale A, the scale rho minus 1/3, and then the healing length. The corrections in that give you this LHY correction, the correction in the wave function, and actually in the correlation between two particles is exactly happening at the healing length. So the healing length is important in order to understand the Li, Huang, Yang correction. So here are the main results that I would like to discuss. This is the joint work with Søren Fournet, this theorem. It's a lower bound that gives you the Li, Huang, Yang correction. So we prove, and there was a published paper in the Annals in 2020 where we proved this for L1 potential. We very recently, so to those of you who have heard me talk about this before, what's new in this talk is that we can prove this now also for the hard core. So we now have, for a lower bound, the complete result for all positive potentials. You may ask, what if the potential is not positive? Well, then it's very complicated because in general such situations would be unstable, there would be no limit for large particles and so on. But for positive repulsive potential, we can now prove it for all spherically symmetric potentials that are values from 0 to infinity, and we only need to assume that they're measurable. I'm here writing with sufficient decay, and the decay has to be just slightly better than being integrable. I mean, slightly faster decay than being integrable. Right? So I'm writing it as the LHY rho of A. This is this expression here. So we now have a lower bound proving this. Unfortunately, the upper bound is not known in that generality. I mean, usually it's easier to prove an upper bound because you just have to come up with the right trial function. But it's not that easy, in particular not for the hardcore. So what is known for the upper bound is that we do have an LHY correction, but you need to assume that the potential is L3. Now, this was first proved by Yao and Yin. I can't remember if they were really so precise about saying what the integrability condition was, but there was recently a paper by Bastis and Ancempo and Schlein where they make the L3 very precise. And I would think that one can also extend this to L1. New ideas would be needed if you would want to prove the upper bound for a hardcore potential. And in fact, for the hardcore potential, Dyson's old paper from 1957, to the best of my knowledge, is still the best upper bound. He does not get the LHY correction. So he does not get square root rho a cubed. He gets an error that's rho a cubed to the 1/3. But as far as I know, this is the best known correction in the upper bound. As I just mentioned before, there are also conjectures that you can go beyond the Li Huang Yang, beyond the square root rho a cubed, and still get a universal formula. And this was already back in 1959, 2 different papers by Wu and a paper by Hugenholz and Pines, where they actually get the next term to be rho a cubed with a correction that's logarithm of rho a cubed. From a rigorous point of view, I think we are still very far from proving this, but there's a suggestion that the universal asymptotics could go beyond the Li Huang Yang formula. Okay, so let me say a little bit about how this has been tested experimentally. Now, in fact, experimentally, the assumption that you're looking at a repulsive potential may not be entirely satisfied, but let me not get into that. The experiment has been done with lithium-7 atoms, that's a boson. You can tune the interaction by using these Feshbach resonance methods, so you can actually tune the scattering length. What is done is that you're putting it in a cylinder, you're confining it in a cylinder, and then you might ask, is it then really a thermodynamic limit as I'm looking at, or is it really more like a confined situation? And in fact, that's slightly unclear. I mean, I'm putting the data down here. So the radius, the distance in the z, that's a cylinder, and in the z direction, it's about, it's about 100 micron, whereas in the radial direction, it's only 5 micron. It is certainly dilute. Rho a cubed is 10 to the minus 3, but the healing length is actually around 1 micron, which is not that much smaller than 5 microns. So it's quite a bit smaller than 100, but maybe it's unclear whether this is really a thermodynamic situation or not. But at least that's the experimental setup. And then it was tuned to 2 different scattering lengths. So that's not much in order to establish universality, right? We would like to show that no matter what type of potential we have, it depends only on the scattering length. So we'll be looking at 2 different scattering lengths to see if we get the same thing. And so one case was 1,400 times the Bohr radius, and another one was about 2,000 times the Bohr radius. And what you see here, in fact, so what's graphed, this is taken from a paper by Navon et al. From 2011. It's not quite the energy, it's rather the energy per volume, it's rather the pressure, which is the Legendre transform, but written in dimensionless parameters, it looks essentially the same as what we had before. It's this formula here. There's a nu squared, which is the leading term, and we see again the 128 over 15 square root of pi, square root of nu, and the dashed line here is the nu squared, and then it's corrected down to the green dots here. And you see that the correction seems to agree quite well with the Li Huang Yang prediction. And in fact, you can then try to find out what is then the experimental calculation of this number, which theoretically should be 128 over 15 square root of pi. So the numerical value of 128 or divided by 15 square root of pi is 4.8. And experimentally, you arrive at, I mean, when you just match how much you go below there in the two cases, you arrive at 4.5 with an error which is 0.7. So that's actually pretty good. Also taken into account that it is maybe not entirely a thermodynamic limit that we are looking at. Unfortunately, it has not been studied, as far as I know, much more experimentally than these experiments from 2011. Let me briefly tell you some of the more recent rigorous results. I told you about Dyson's work from 1957, the work by Lieb and Ingwerson from 1998 on the leading term. So here I'm talking a little bit about the rigorous work on the Huang Yang term. So there was, back in 2008, a very remarkable paper by Erdős, Schlein, and Yao, where they first sort of used Bogolyubov, motivated by, well, I don't know, but if you read the paper, it seems that they were motivated by the Bogolyubov approximation to write down a trial function, which actually gave an error of the right order as the Huang Yang. So they don't get the right constant, but they get big O of square root rho A cubed. They need somewhat stronger assumptions on the potential V that I've been discussing here. Then in 2009, Giuliani and Zeiringer looked at soft potentials, where you imagine that this potential spreads out at distances much bigger than rho minus 1/3. Well, you can still fix the scattering length to be rather small, but the potential is very much spread out. So they called it dilute but high density, right? Because the potential was spread out so that many particles interacted with each other, but it was still dilute seen from the point of view of the scattering length. And in that case, they actually prove the Huang Yang formula for such potential. But notice that the potential then depends on the number of particles, on the density in that limit. Boccato, Brennecke, Senancempo, and Schlein, in a series of papers, but maybe the last one was in 2018, actually proved the Huang Yang formula in the confined case. So they confined to a box the size of the healing length, and then they actually prove. You have to readjust the scattering length in that case, but they actually then prove the Huang Yang formula. With my PhD student Britzke in 2019, we sort of generalized the idea of Giuliani and Zeiringer of the soft potential, the potential that may depend on the density, to allow that it had not high density. I mean, so we took a radius of the potential much, much bigger than the scattering length, but much, much less than rho minus 1/3. Still depending on the density. So when I say A over A much, much less than R, I mean that in the dilute limit, R divided by A would go to infinity with a certain, at a certain rate. So we could still not have say, anything close to the hard core, or just a situation where R was of order A. Then the same year, Britzke, Fournet, and myself, we gave a lower bound with a relative error of Huang Yang, also for the hard core. But that work is now obsolete because we can now not only get the Huang Yang order, but we can actually, as I stated in the main theorem, Fournet and I can now prove the full Huang Yang correct constant also for the hard core. Let me just mention that there was a model suggested by Lieb in 1963 that has been studied a lot recently by Carlin, Jocelyn, Lieb, and Holtzman, different combinations of those authors in a series of papers. And Lieb already noticed in 1963 that this model actually recovers the Huang Yang correction. The problem with the model is that its connection to the true quantum mechanic many-body problem is, I mean, the rigorous connection between the two is not well established. Okay, so now let me tell you about the Bogolyubov approximation and how it leads to the Huang Yang formula, or how it almost leads to the Huang Yang formula, and what you need to do to make it rigorous. So if we are, and I'm trying to do this without doing second quantization. So That's a choice. I didn't want to introduce, I will actually introduce something like creation and annihilation operators in a moment, but at this point, I'm trying to avoid it, also because it's then easier for me to explain the rigorous adjustments you have to make. So we're looking at the box, again, the box with side length L. Let P be the projection onto constant functions in the one body, in the L2 space. What is the role of constant functions? Well, think of periodic boundary conditions, right? In periodic boundary conditions, the constant function is the zero energy function for the Laplacian. So if there was no interaction, all the particles would just go and become a product state. The wave function would be a product state of the one. I mean, the ground state will be one, and I'm thinking of one being a product of ones. Right? So the projection onto the constant is of the projection onto the ground, or it is the projection onto the ground state of the free Hamiltonian, the one-body free Hamiltonian. But what is going to be important is that that will not be the correct thing, of course, when I have interaction, so I'm also introducing the orthogonal projection, Q. And I'm writing the number of particles. Well, the number of particles is 1, if you want the operator 1, sum from 1 to n, that's the number of particles, but I write the 1 as a sum of p and q. And pi means the projection acting on particle I, and qi means the projection, the q acting on particle I. Right? And then I sum I equal 1 to n. And this, this first term, the sum over pi, I call n0, and the sum over the qi's, I call n plus. Now, the n0 is an operator. And it's actually the operator measuring how many particles I have sort of in constant functions, right? If I'm looking at the ground state of the non-interacting problem, n0 would be n. N is fixed, n is a number. But n0 is not a number. It will fluctuate. It will have sort of a distribution in the ground state. And n plus will have a distribution in the ground state. But their sum is a fixed number. So the Bogolyubov approximation, the first step that Bogolyubov says is that we have condensation. And condensation is essentially saying that n0 is the same as n. That's not entirely true, because there are particles that are thrown out by the potential, and that will give us the n plus. So the n plus is the difference here. But to leading order, n0 should be of order n. Not just an expectation value. I mean, it should even be that the fluctuations are rather small, or rather the fluctuations of the n plus, that they are rather small. At least that's something one would have to control in order to do a rigorous proof. Anyway, so that's the first step in the Bogolyubov approximation. I'm not making it entirely precise, but that's the first step. The second step is to take the many-body potential V and expand it. So, I mean, remember, this is a two-body potential. So I can actually, so it's acting on the two-body space. So I can put one tensor the identity, one tensor 1 on the left of V and one tensor 1 on the right of V. I mean, V maps two particles to two particles, and two particles means that I'm actually looking at the tensor product of this L2 of omega L with itself. Right? I'm writing one as P plus Q, so I have P plus Q tensor P plus Q to the left of V and P plus Q tensor P plus Q to the right of V. And then I can expand. That would be 16 terms, 2 times 2 times 2 times 2. Right, and I've written out 2 of the 16 terms here. There's the PP, VP, P term, and then there's the last one, the Q, Q, V, Q, Q term. So this means all the excited particles, the particles not in the condensate interacting with each other, and these are all the particles in the condensate interacting with each other. And then Bogolyubov, in his famous 1947 paper on superfluidity, says we should ignore, so not only should we think of n0 and n being the same, because n plus is very small, we should think of the q being very small, and we should ignore all terms that have 3 and 4 q's in them. And that's, so that's a lot of the terms in here. Now, it turns out that there will be no terms with just one q. because of translation invariance. I mean, if you have pp on the left and pq on the right, because pp has momentum 0, you cannot have pq on the right. So there are no terms with just one q. Okay, so now it turns out that you then only have terms with 2 q's or 2 p, I mean terms with 0 q's, pp, v, pp, that can just be calculated. This is just some integral. It's just a number, basically. And then you have the terms with 2 q's. And the terms with 2 q's can be diagonalized. And I'll explain in a second how to do that diagonalization, at least at a very formal level. But the answer when you do this is the following formula, or at least to leading order, or to next to leading order in the dilute limit. So you're getting an integral, and I'll explain where this integral comes from. And there's an A0, it's not an A, unfortunately. It's not the scattering length, it's an A0. And A0 is simply the 1 over 8 pi integral V. And if you remember back to one of my first slides, that could be much, much bigger than the scattering length. It could actually be infinite if it's the hard core. But then I've actually, the term in red here is a term that I added and subtracted. I mean, not quite. I mean, the A1 is the term written here. This is this integral v hat of p squared over p squared, whereas up here, I have actually replaced the v hat of p by v hat of 0, which is the same as the integral v. So I've taken a certain approximation to the integral over there. Now, it turns out that this term will make this integral convergent. So I can actually calculate that integral. However, it looks like we're actually getting something that could look like Huang Yang. It has the first term 4 pi rho squared times something A0 plus A1. Notice that the A1 is actually a negative, so it pulls down the A. But for the hard core, it will still not be very well defined. But in fact, the A0 and the A1 are the first 2 terms in what's called the Born series for the scattering length. So it's not the scattering length, but it's a fairly good approximation to the scattering length if the potential is soft. I mean, if the range of the potential is much larger than the scattering length. Now, if I replace A0 plus A1 by the scattering length, and if I replace A0, I do that in the first term, in the term up there. A0 plus A1, I'm just doing it. I'm just replacing it by the scattering length. And in this integral, I'm also replacing A0 by A. Then I will actually get the Huang Yang formula. I'm not telling you that we can do that. In fact, that's the whole problem. I have to prove why we can do that. So if we do Bogoliubov, that's what we would get. It would not be the right answer, but it's sort of suggesting what should be the right answer. Let me just show you where the healing length comes in. So let's look at this integral here. And in the integral, let me do a change of variables. And here you notice I put in this rho A0, square root rho A0. If A0 is A, that's essentially a healing length change of variables. I'm changing variables into so that the momentum is of order 1, but the p that I had in the original integral is then of the order of the healing length. And then you will end up with an integral, just a plain integral, a number that can be calculated, and you will end up with 128 over 15 square root of pi. So that's where the number comes from. I just have to understand why the A0 and the A0 plus A1 can be replaced by the scattering length. Let me say one word about where this integral came from. I don't want to spend a lot of time on it. It comes from the Bogoliubov approximation, or the way one diagonalizes these terms with 2 q's. Now, it turns out that the term with 2 q's, if you write them out in second quantization, they can be written as an integral over momentum of an operator which essentially looks like this. There will be terms A star A and A star A, a plus and minus, 2 types of terms corresponding to momentum P and momentum minus P. You have these pairs with momentum P coupled to momentum minus P. There's a way to write the Hamiltonian like this. And then there will be, so these terms actually correspond to having P and Q, P on the left and P and Q on the right. If you have PP on the left and QQ on the right, you will rather have terms of the form A star A and AA. There's a way of writing it down. The whole point is that a Hamiltonian of this form you can complete a square. I mean, if you assume that these operators commute with each other, you can complete a square, and you will get that there will be a term which is B star B, B star B with a positive constant. This thing will be a positive term. And you can bound the operator from below by something of this form, each momentum P. And when you do the integral over P, you will get something like this integral that we found here. I mean, some number minus the square root of something else. You can do this calculation yourself. It's not that difficult. Here, I did not assume that A and A star were creation and annihilation operators, but if they are, then these numbers are ones. So you'll get a 2 that will cancel the 1/2, and you get something which will exactly give you the integral. Now, this was a lower bound. I did this by completing a square. I had ignored this term here. But actually, you can show that if they are creation and annihilation operators, then this is correct. This is the right thing. And Bogolyubov actually used this term here to explain superfluidity, because this D will then give you something about the excitation spectrum. That's not what I'm interested in here. I'm only looking at the ground state, but you would get the excitation spectrum. And from a linear behavior of the dispersion law, Bogolyubov and Landau explained superfluidity. Okay, so now the last 2 slides, last few minutes that I have, let me explain what is wrong in the Bogolyubov approximation and how to correct it. Now, what's wrong is that we cannot ignore the terms with the 3Q and the 4Q. Remember, that was what I said before. We wanted to get down to terms with only 2 Qs. But that's not going to work, because those terms with 3 Qs and 4 Qs will contribute to get the right scattering length. So we cannot do that. And in fact, in the work with Fournet, we identified the term that can be ignored. And it's this quadratic expression. So actually, Søren Fournet, who gave the Laudatio when I received the Poincaré Prize, mentioned that the proof here was essentially 2 completions of the square. And I just gave you the first one, which was Bogolyubov, and this is the second one. I mean, this is not quite fair, I think, because the paper is almost 100 pages. But except for that, you see, you put in, there's the scattering length coming in here, the scattering function, sorry. We identified this term. This term is positive, so you can ignore it. So what we do is we add and subtract this term, then we ignore the addition, which is positive, right? It's and then for the negative, it actually removes the 4Q terms, but it renormalizes all the other terms, the 3Q and 2Q terms. Now, the 3Q terms, we can still not ignore. Even the renormalized 3Q terms, we cannot ignore. They will contribute. The reason is, and I'm trying to explain it down here, I'm saying that the 3Q terms, they will now look like this. Ignore the low and the high for the moment. So there will be 3Q terms of the form PQ, QQ. This is a term with 3 Qs. It's no longer just a V there. It's 1 minus omega V. That's the thing that has been renormalized by putting in the omega there. Right? And now, if you remember, 1 minus omega was the scattering solution. So instead of having a V, I now have the scattering solution times V. And the integral of that is the scattering length. So I somehow managed to get to the scattering length, not to go to infinity if it's the hardcore. Now, so we want to understand terms like that. It turns out you only have to look at the situation where on one side you're projecting onto low momenta and on the other side high momenta. And let me just heuristically try to explain why that's the case. You have these pairs created from the QQ. They live at the distance of the healing length. On that distance, they see lots of other particles in the condensate. And they actually see the correction. They don't just see condensate, they see a correction from the condensate. And that's exactly why one has to put in this low part here. That has to contribute in order to understand the right thing and get the scattering length. But this you should again think of in the high momenta as a 2Q term. It's a 2Q high term. And then you do Bogolyubov one more time. You Bogolyubov diagonalize for the high terms, and then you end up with that everything will be the scattering length at the end. What I explained just now was how to get the second step of Bogolyubov. I mean, how to not ignore the 3Q and the 4Q terms. I did not explain to you how to get to the condensation, which was important, the fact that n0 is of order n, that n plus is small. This we cannot do in the big box. I mean, we have no way of controlling condensation in the big box. It may be true, but we don't know how to do it. But the way we do it rigorously is to localize to boxes that are much, much smaller than the universal box, not the omega L, but a box of some much smaller length where the new length is just essentially of the order of the healing length. You cannot go to the healing length, you have to go to, because if you go to the healing length, you're going to destroy the problem. Everything is happening on the healing length scale, but you go to a much larger scale. So a large constant in terms of this diluteness parameter times the healing length. You localize to that scale, and then you do the whole analysis. So that's how the rigorous proof goes. I have not said anything about how we get to the hard core, because all of this will essentially just work for L1 potentials, but we will approximate the hard core from below by an L1 potential, and by controlling the fluctuation much better than we did in our first paper, we can actually approximate from below to an accuracy so that the approximation is good enough for the scattering length and still get all the arguments to work. It's a much more complicated argument, and we had to rewrite our whole paper again. What are the main open problems? Well, from my point of view, it's to get the upper bound for the hard core. I mean, to finally complete this analysis from 1957 for all positive potentials. You may ask, what about positive temperature? Or you may ask what's happening in other dimensions. Those two problems may actually be simpler than the upper bound for the hard core, but that's all I wanted to tell you. So thanks a lot for your attention.
Thanks, Jan-Philipp, for this very nice lecture. We have time for some questions. Volker?
Yeah, I'm wondering, I have a sort of not a mathematical question in a sense, more about speculation. What do you think is absolutely important for the model that enters, like using the Laplacian? Could it be replaced by some other operator that, for instance, does not have a positivity preserving semigroup? You know, you don't have possibly a positive ground state. Or what if you change from the fixed n to the chemical potential? How does the picture change that you get? Can you comment on this?
So the last question is the easier one. I mean, if you do the grand canonical formulation, in fact, that's what we do, because we had to localize to these small boxes anyway, and during the argument to get condensation. And when you localize to a small box, you've lost the number of particles. I mean, you no longer know what the number of particles, what it is, in the small box, right? Because particles move in and out of the boxes. So in fact, in the large box, we go from the canonical formulation to the grand canonical formulation from the beginning. Those two are equivalent. And then we actually do. So there's no difference between canonical and grand canonical. For the other question, the short answer is I don't know. We use a lot about the Laplacian. Localization is incredibly important. We use very specific properties of the Laplacian. So I would not know. I mean, one could think about what if there are magnetic fields in there. That would definitely complicate the situation. That's all I can say.
Can I just add up one more question? How does it relate to the work of Girardot, who has carried out a kind of Bogolyubov-Hartree-Fock approximation for these models?
I mean, so I don't know exactly what Girardot did for this model. I know his work in one dimension, but so with Robin Roivers and Marcin Napiakowski, we studied a variational model where you don't do Bogolyubov approximation, but you instead say that if you believe in the Bogolyubov approximation, then the ground state of this 2Q, the quadratic Hamiltonian, would be a quasi-free, or what is sometimes called a Gaussian state. So we said, let's turn it around. Let's not change the Hamiltonian, but let's restrict the way you would do in Hartree-Fock theory. Let's restrict to quasi-free states. We also, and this is what we originally did in our paper for fermions for the Hubbard model, so we tried to do the same. We restricted to translation invariant states in the thermodynamic limit, and we analyzed it, and you do not get the Huang Yang formula. You get some other formula, because you get the same error that Bogolyubov is getting. You don't get the scattering length. However, you get the scattering length for the leading order term. You don't get just the Born series. You get the scattering length. And that's essentially what was discovered in this paper from 2008 by Erde, Schlein, and Yao. But for the Huang Yang term, the second term, you get something much more complicated. Depends on V in a complicated way, but in such a way that if you converge to a soft potential, then you recover the Huang Yang formula. But you can do the positive temperature, and you can analyze this whole model.
There was a further question up there. Yes, please.
Yes, thanks for the talk. I wanted to ask, you have this universal asymptotic law for the ground state, and the question is, is it known that at some point this law cannot be universal anymore, so you need more explicit information about the potential than just the scatter lengths and the other universal parameters you have?
Oh, you mean if you go away from the dilute limit? Yes, definitely. I mean, if you go to high density, if you think of a potential that's L1, and you go to high density, then in fact the leading order term would be, so the leading order term in the dilute limit was 4 pi rho squared A, but if you go to the high density, it would be 1/2 rho squared integral V. I mean, also, if you think of the hard core, if you go to high density, of course, that's not even possible for the hard core, right? Because at some point they will pack. But if you had an L1 potential and you go to the high density limit, you would certainly no longer see the scattering length coming.
No, I was interested in if you're still in the dilute limit, but to some order, it cannot be described by the universal parameters anymore. And
you're asking if in some asymptotic sense it can no longer be, I'm pretty sure that yes, that this would not be possible.
Yeah, okay. Thank you.
Are there any further questions or comments? Yeah, maybe we'll take one more. Yes, please. Go ahead.
I just had a naive question about the temperature. When you turn on the temperature, do you expect also a perturbative expansion on the free energy?
I expect that there is a formula also in the dilute limit at positive temperature. And I expect that it is what you would get by looking at the model I described before, this Gaussian model, but again, where you have to sort of replace the fact that you're not getting the scattering length coming in directly, but you're getting the same type of errors that Bogolyubov got. But in fact, Robert is the expert in doing the positive temperature, so maybe he should answer the question. Yes, but I think there is an expansion in the dilute limit also at positive temperature.
Okay, so I suggest in the interest of time, so that people can still make it to the human rights panel, which is starting just about now downstairs. So we'll close this session, and we'll thank Jan Philipp again for the very nice lecture.